Okay, so what we're going to talk about now is we're going to talk about using your plus pack, your extra sensors and cables to do an AV smoothness test. Alright, so in order to do that, we're going to have to download a video. So we can see here from the downloads section, right under the application, at least in this current version of the website, we have a link to download a video which can be used for AV smoothness test, which is possible with the plus pack. So it says here to right click and select save link as, because if we just click on it, it will start playing it in the browser. I'm going to do this, save link as, and we can download it, and we can save it anywhere you want. I'm going to save it to my downloads folder. In this case, I already have done this, so you can see if I click save, it will save it there, but I'm going to be able to save the time of doing that because I already have it downloaded. So it's a 340 meg file, and so I'm going to go ahead and just start this up here and talk about this video a little bit. Now, this video is specially made to be a 30 frame per second video, and those circles, there's a change every single frame, but only one of those circles will change per frame. So unlike a binary pattern where both can change at the same time, this is called a gray pattern. So the pattern is actually black, 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 white, then white, white, and then white, black, and then back to black, black again to start. So as you can see, that differs from the binary pattern. Now, let me just briefly mention why I have my sensors hanging so low here. In Windows, it's very convenient and easy to just drag my window off to the edge, and as you can see, it resizes it to half the screen width, and it just so happens that I've positioned my sensors so that they'll be over those changing circles when the video is played in that size. You can play it full screen if you want and move your sensors up and put them up higher, and that's fine. But one more thing that I need to mention before we go any farther on this is the refresh rate of your monitors. Now, as we just said, that video was specially designed to be exactly 30 frames per second. Okay? And typical frame rate for the wireless display is 30 frames per second, so that should be fine. And in fact, it's showing here that that's what our refresh rate is for the remote. Okay? And for the local, what we need in order for this test to work properly is we need this to be some multiple of 30. So in this case, we want 60p. Now, if we had 50p, which it was, then it would not work. The gray pattern would not be uniformly detected in the calibration, and it would just plain not work. So I'm going to set this to 60 hertz here, 60 progressive hertz, and I'm going to apply that. Yes, and I'm going to close this. So that should work now, and so now we can move on to launching the LatencyPro and starting the test. So here we go, the LatencyPro application again. Again, like with the latency test, this one will do an auto calibration when you start, and For the audio, this is a little bit different here. Instead of having an audio tone when there's a transition, we're going to play a continuous tone. And so what we're looking for in this case is we're looking for breaks in the audio. So this is looking for smooth playback of both audio and video. And so we will be able to detect gaps in the audio. If there's some audio packets that are lost over the Wi-Fi, or if there's some problem encoding or playing back and there's a gap, we should be able to detect that. Now, the reason we have these sensors on both screens is in case somebody has some problems with the local playback or something like that, we should be able to detect that as well. And so if there happens to be a glitch in the media player that's playing the video and it has a skipped frame or something like that, we certainly don't want to assume that that is a result of the wireless display transmission. So I'm going to go ahead and start this and take a look at it. Okay, so just as we had in the case of the latency test when we ran it the first time, we have these windows getting created up here, which is blocking our sensors. So we need to go and find the first window, which I believe is this one. Actually, I'm not sure, but I think it was this one. So I'm going to size this down a little bit, and I'm going to hit the tile. No, it's this one. So this was the one it put up in the top corner, so I know it's the first one. Quad tile, and there we go. Okay, so what we're seeing here, we're going to have to restart this test, of course, but what we're seeing in this case, we have a black-white pattern. So this will capture the data and plot the black-white pattern, and this will capture the time between frames. Okay, this one should be 33 1/3 or so milliseconds between frames. This is the local. This is local, and this is the remote, and then this is the audio. What we're reading here on the audio is every 25 milliseconds we're going to report how many cycles we captured. Now it just so happens that the audio is 1 kilohertz audio, so in 25 milliseconds we should have counted 25 cycles. Okay? And then what will be captured over here is gaps. So if we happen to capture a gap of audio greater than, I think it's 25 milliseconds, then that data point, the gap size and the time it occurred will be captured here. And you can then go and correlate that with the interframe times and the black-white patterns and see if the audio glitch happened to correspond with the video glitch. So I'm going to go ahead and restart this here now. And I don't want to save any of that data. And here we go. Alright, so this is looking pretty good right now. I would expect this to be pretty clean. In a clean Wi-Fi environment here. Not an RF chamber, but it's relatively clean. Now as you can see, this pattern here, it goes from 0 to 1 to 11 to 10 back to 1. That pattern should repeat itself. Okay, and we're not seeing any audio glitches. Alright, but I I'm going to just do a little, I'm going to mute the audio here briefly, and there we can see a glitch there. Mute the audio again, and we can see that we're getting some report of audio loss here, and so I'm going to go ahead and stop this data. The data collection stopped after 60 seconds. So now I'm going to go ahead and shut this down, and it will save our data. So I'm going to just go ahead and put it in that downloads folder again, and I'll make a folder called AV Smoothness. I'll save the data there. Alright, now we can take a brief look at the data and discuss what we're seeing. Okay, so I removed the sensor so that doesn't block our view. So the black-white pattern, 0 black-white pattern, is for the local display. And look at that. So here what we have is we have timestamp in column 1, and then we have the pattern in the second column. So as I said, 0, 1, 11, 10, 0, 1, 11, 10. That should be repeated as glitch-free as possible, okay, hopefully. And the next thing we have is the interframe time. Okay, so the interframe time, as I said, should be around a third of a second, or I'm sorry, 33 milliseconds. Okay, and so as we can see, it is pretty close to that. Okay, now since this was pretty clean, it's going to look pretty much the same for the remote. And again, we can see the 33, so that's pretty good. And then the audio gap, we artificially introduced some audio gap there. So we captured that. In this case, it was 1.6 seconds. And the second gap looks like was about 3 seconds. Those should be somewhat visible in here, but it's more direct and easy to just read it from here. So that's what that data looks like. Obviously you can take this data, you can write some scripts to process it, you can graph it, and but this is the raw data from which you can analyze your AV smoothness.